Welcome to the presentation of our work on meta-tuning loss functions and data augmentation for few-shot object detection. In few-shot object detection, the main goal is to learn a generic model over the training set of base classes such that the detection model for a new object category can be built based on a small set of its annotated samples. Our work is motivated by the simplicity and success of fine-tuning based few-shot object detection approaches, which simply use gradient descent to adapt a pre-trained object detector. However, this fine-tuning framework does not provide a mechanism to learn inductive biases specifically for training with few samples. In our work, we propose to inject few-shot specific inductive biases into the fine-tuning procedure based on meta-learning principles. More specifically, we propose to tune loss function and augmentation details via reinforcement learning over proxy tasks. We can now take a closer look to the details of our approach. To put into context, most few-shot object detection approaches can be grouped into two main groups: meta-learning and fine-tuning based methods. Meta-learning approaches aim to learn a dedicated meta-model that maps a given set of trained samples to a detection model or an easier-to-adapt meta-model. While meta-learning provides a principal training framework, there is a risk of overfitting to the base classes, and it is often difficult to interpret what is actually learned. In contrast, fine-tuning based approaches tackle the problem as a typical transfer learning task by adapting a pre-trained model via gradient descent. Despite the simplicity and generality, they yield performance competitive to meta-learning based approaches. However, unlike meta-learning, they do not offer a mechanism to acquire inductive biases specifically for few-shot learning. Based on these observations, we propose the idea of meta-tuning for few-shot and generalized few-shot object detection problems. Our goal is to improve data efficiency of the fine-tuning based training by end-to-end optimizing the training pipeline details. The key idea is to apply meta-learning principles to tune the loss function and augmentation details in an end-to-end manner. In conventional fine-tuning based few-shot object detection, a pre-trained detection model is updated using a simple gradient descent based pipeline over the few-shot training set. We extend the fine-tuning scheme to construct the meta-tuning mechanism. We start by defining a Gaussian distribution for each augmentation and loss function detail that we want to model. To meta-learn these distributions, we define an episodic training procedure that samples proxy few-shot detection tasks over the base class training data to imitate real few-shot detection tasks over the novel classes. Each proxy task contains a few-shot support set and a query set. At each proxy task, we sample an augmentation and loss function and fine-tune the initial model on the support images using gradient-based optimization. To evaluate the effectiveness of the sampled augmentation and loss functions, we apply the resulting few-shot object detection model to the proxy query set and evaluate its MAP score. We get multiple MAP scores by repeating this process over multiple proxy tasks. Finally, we update the Gaussian distributions that parameterize the augmentation and loss functions by using the normalized MAP scores as reward and applying the reinforce update rule. Prior work suggests that the classification components are typically more problematic than the localization ones in few-shot object detection problems. Therefore, our specific focus revolves around refining the classification loss components of the detection models. Within this classification loss, a crucial parameter is the softmax temperature. We define two alternatives for meta-tuning the temperature. The first one uses constant temperature, which is represented by a single Gaussian distribution. The second one defines a dynamic temperature defined as a function of fine-tuning iteration index. Here, we model this function by a second-degree polynomial whose coefficients are represented by separate Gaussians during meta-tuning. The learned temperature function can increase or decrease the temperature during fine-tuning and make the class prediction smoother or sharper. We also define a novel class score scaling coefficient to learn the score balancing during meta-tuning. Finally, we apply the meta-tuning idea to the data augmentation magnitudes as a single normal distribution. We focus on photometric augmentations based on brightness, saturation, contrast, and hue, and define a single shared Gaussian to model them jointly during meta-tuning. In reinforcement learning, we focus on only the mu values of the Gaussians to simplify the distribution models. We initialize Gaussian sigmas to 0.1 and diminish them over the reinforcement learning iterations to improve convergence. We update mu values according to the reinforced rule. Here, R represents the reward value obtained from normalized MAP scores over a sampled set of proxy tasks, and P represents the Gaussian probability density function. We can summarize the meta-tuning procedure with this algorithm. Here, we reinitialize the model weights for the new set of proxy tasks and sample a set of loss and augmentation function pairs based on the current Gaussian distributions. We fine-tune the initial model based on each sampled proxy task. We whiten the MAP scores, select the maximum value as the reward, and make a single reinforced step to update the distribution of loss and augmentation functions. We perform our experiments for few-shot object detection and generalized few-shot object detection problems. We use harmonic mean metric for the generalized few-shot object detection experiments. We compare our approach with other fine-tuning based methods. Here, MPSR and DFRCN are the fine-tuning based few-shot object detection baseline models that we adopt. We report the average scores obtained for varying number of shots in both standard and generalized detection settings. We can observe that meta-tuning obtained the top results among the fine-tuning based few-shot detection methods. Similarly, on the MS-COCO dataset, we obtain clear gains over the MPSR and DFRCN baselines and obtain results comparable to or better than the state-of-the-art in fine-tuning based few-shot object detection. Finally, we look into the dynamic temperature functions learned by meta-tuning over different data splits. We observe that temporally attenuated temperature values are preferred consistently, sharpening the predictions towards the end of the fine-tuning process. The interpretability of these outcomes highlights a significant advantage of the meta-tuning framework. To sum up, we provide a first attempt to learn loss function and data augmentation parameters for few-shot object detector training. The experimental results indicate the effectiveness of the proposed scheme. More details and additional experiments can be found in the paper.